So let's look at examples of this and using this multiplication rule. Say a bag of marbles contains 10 blue, 7 red, 4 green, and 1 yellow marble. So we've got lots of marbles here. Let's add them all up. The total will be 10 plus 7 plus 4 plus 1. That's 22 marbles altogether. Part A. What is the probability of randomly picking 2 blue marbles from the bag if you replace the first marble before drawing the second? So notice there's a key word here. We're going to replace the first marble before drawing the second. So if we replace the first marble before drawing the second, the bag stays exactly the same. So when I go to calculate the probability of these two random events, or randomly picking, I should say, 2 blue marbles, we're going to multiply the individual probabilities of picking a blue marble together. So first off, picking the first blue marble, there's 10 blue marbles out of 22. And then remember, before the second pick, you replace your first marble, mix them up, and draw again. Because you've replaced the first marble, the bag stays the same, so there's still a chance of 10 out of 22 to get a blue marble. So here, the two probabilities that you're calculating with are exactly the same because the bag stays the same. And so drawing a blue marble the first time is the same as drawing a blue marble the second time. To calculate this, go 10 divided by 22 times 10 divided by 22, and that will get you approximately 20.7%. So you've got about a 20.7% chance of picking 2 marbles from this bag. Part B, let's change the problem just a little bit. What is the probability of randomly picking 2 blue marbles from the bag if you do not replace the first marble before you pick the second? So you do not replace the first marble. So if you do not replace the first marble, then things will have changed about the bag. So your initial pick is going to be the same. You are starting with the whole bag, so picking a blue marble is 10 out of 22. But when you pick the second marble, the bag has changed. You no longer have 10 blue marbles. You have 9 blue marbles to choose from. You no longer have 22 marbles. You have 21 marbles. Because once you have taken a blue marble out and not replaced it, what has happened is that your numbers have changed. You now have 9 blue and 21 marbles total. So that's why the bag has changed and your probability changes. So now our calculation will be slightly different. It's still similar, but slightly different. 10 divided by 22 times 9 divided by 21 is approximately 19.5. Notice the probability of getting 2 blue marbles now is slightly lower than it was before because on your second pick, you have less blue marbles to choose from. All right, let's look at another example. A holiday light string of 20 bulbs contains 3 defective bulbs within it. We don't know where they are, we just know there's 3 of them in this group of 20 bulbs. Let's look at the following questions. What is the probability of randomly choosing a defective bulb? Now we're talking about A, which is 1 defective bulb, so we're just looking at a single probability. So we just think about how there are 3 defective bulbs out of 20 altogether. That's it. 1 fraction for 1 event. 1 fraction for 1 event. 3 divided by 20 is equal to 15%. So we've got a 15% chance of choosing single bulb and having it be defective. Now, in the next question, though, I ask about choosing 2 bulbs and having both of them be defective. So now we've got 2. So because we've got 2 bulbs, we're going to use the multiplication rule. We're going to start with picking a single defective bulb because we want both of them to be defective, so our first bulb has to be defective. That's going to be the same as we did in part A. There's 3 defective bulbs out of 20. But when we go to pick our second bulb, because we've picked a defective bulb out, at least we've specifically set up our probability that we did, we are going to only have 2 left to pick from. it didn't say here that we replace the bulb, and unless you see something in the problem that says you replace a bulb before you pick the next one, we assume there is no replacement. So there are only 2 defective bulbs left. We have lost one of them because we've picked it. So we've had 2 defective bulbs left out of a string that only has 19 bulbs left because we picked one of them out. So the string has changed when we take one out. So our second probability has changed. So 3 divided by 20 times 2 divided by 19 would give us 1.6%. So there's a 1.6% chance of picking 2 defective bulbs. All right, our next question says, what is the probability of choosing 3 bulbs and having all 3 be good? In other words, none of them are defective. Now, our multiplication rule works for more than 2 events. You just continue to multiply another probability on for however many events you have. So if we're looking at choosing 3 bulbs, that would mean we multiply 3 probabilities together to create our overall chance of choosing 3 bulbs with those qualities. Now we want them all to be good this time. If we have 3 defective bulbs, then out of 20, that means 17 were good out of 20 on the first pick. But as we go to our second pick, we've lost one of those good bulbs, so now we only have 16 good bulbs out of 19 in the string because we have one less bulb. And then on our third pick, we only have 15 good bulbs left out of 18. So we have to adjust our second and our third probability based on the fact that the string of bulbs is changing. So when we do that calculation, 17 divided by 20 times 16 divided by 19 times 15 divided by 18, and I recommend putting it all into the calculator at once, you get 59.6%. So there's a 59.6% chance of picking 3 good bulbs. All right, it's a good idea to do more examples, so let's do some more. Let's say we have a spinner for a board game that has 5 colored regions, and I've got a picture here kind of showing that. It is equally likely that the spinner will land in each of the 5 regions that you see here. Notice there's 2 regions that are blue, 2 that are green, and 1 that's yellow. So what's the probability of getting a blue, spinning and getting a blue? Now notice, I just say getting blue. I don't say spinning twice, spinning 3 times. I just say getting blue. So that implies once. So we have one event here. So that would be 1 fraction for that probability. So there are 2 blue regions out of a total of 5. So our probability would be 2 out of 5. 2 over 5 is the same thing as 40%. We've got a 40% chance of getting blue in a single spin. But what if you spin twice? So if we spin twice, what's the chance we get blue both times? So if we spin twice, we're going to multiply 2 probabilities for getting blue. Well, let's think about the first spin. In the first spin, you've got 2 out of 5 chance of getting blue. In the second spin, has anything changed about our spinner? No, the spinner is exactly the same. The spinner doesn't change as you spin it. Unlike if you draw marbles from a bag and don't replace them, here the spinner is going to stay the same every time you spin it. So the chance of getting a blue is going to stay the same, 2 out of 5. So 2 divided by 5 times 2 divided by 5 is equal to 16%. All right, one more. Let's say we want to look at the probability of getting first a blue and then a yellow if you spin twice. Once again, we're spinning twice, so we are going to multiply 2 probabilities together. You're going to have a probability you multiply for every single event. So because we have 2 events, you're spinning twice, you have 2 probabilities to multiply. The probability of getting first blue, that would be 2/5, and then yellow. Now the spinner hasn't changed, there's still 5 regions. There's only one of them, though, that has yellow, so 1 out of 5. So 2 divided by 5 times 1 divided by 5 gives you 8%. An 8% chance of first getting blue and then getting yellow. Question 4. A study group contains 5 English majors and 3 history majors. What's the probability of selecting 2 history majors to represent the group at a conference? So we're sending 2 people to the conference. What's the chance they're both history majors from this group? All right, so we've got 2 people we're choosing, so that means we're going to multiply 2 probabilities together. We want both people to be history majors. Let's think about the chance of the first person being a history major. Well, the first person being a history major, initially in this group, we've got 3 history majors out of a total of 8 people. However, when we pick that first history major, it wouldn't make sense to pick that same person again. So we now have only 2 history majors out and 5 English majors. I started to slash that 5, but technically the English majors haven't changed. What's changed is the history majors. There's only 2 of them out of what's changed is the total 7. There's only 7 people left to choose from. So the probability of getting 2 history majors going to this conference, if you just randomly select 2 people, would be 3 divided by 8 times 2 divided by 7, which would be approximately 10.7%. So you've got a 10.7% chance of sending 2 history majors to represent the group at a conference. All right, our last example on the slide. Suppose a particular medical test has a 15% chance of resulting in a false negative. False is always something, a false result is not something you want. And this is not, it's not a huge amount, but it's still not insignificant, a 15% chance of getting a false negative. Well, let's investigate the probability of 3 tests in a row giving a false negative. Now, in our previous examples, we knew the data or the situation involved in coming up with a single probability. Here we don't. We don't know how this 15% chance of resulting in a false negative came to be. There was probably lots of experimentation that went into it. There may have been thousands of examples that were used to come up with that 15% chance. All we know is the 15% chance. And when we don't know where the percentage came from, we use the percentage without adjusting it for each of the probabilities I use when I have multiple events. In this case, 3 tests means I'm going to multiply 3 probabilities together. And I'm going to use that 15% each time because we don't know how to adjust it without knowing the raw data it came from. So 3 tests in a row of 15%. We're going to multiply 15% 3 times. Now, when you multiply with percentages, you must convert them to decimals. So we're going to multiply 0.015, oops, I said that wrong, 0.15 times 0.15 times 0.15. And it can be a little confusing having the dot for multiplication here with the decimal. That's part of why I have the parentheses surrounding them, is to try to separate the dot for the multiplication from the dot from the decimal. Another way to write this, if you prefer, would be this is the same number multiplied 3 times. You could think about it as that 0.15 to the 3rd power. That would be another way to do it. So when we calculate that, 0.15 times 0.15 times 0.15, that would be 0.3%. And I have rounded there at the first decimal place. Technically, when I do this calculation, I get 0.003375. And so remember, I move the decimal point 2 places, and then that becomes, when I round, 0.3%. So a little reminder on rounding.